You might remember that last time we sort of wrapped up with scary code. Remember I was showing you how you can allocate or declare a C array and then completely ignore its boundaries and access outside of it. And you can start using that for all kinds of wild and frightening things. And so this is a general issue. C is a great language if you want to write insecure code, because it does very little to prevent you from saying whatever you want or doing whatever you want, whether or not it's actually a good idea. And you'll learn this as you go through this class because we're doing everything in C and it's really easy to write buggy code. The problem is C is also really great for accessing the hardware directly and accessing low-level facilities. And languages that prevent you from making these kinds of mistakes don't really allow you to access that stuff. So that's kind of the problem that we have, is that you kind of have to work in a language that's not very nice. Okay? Maybe Rust will eventually supplant C. I don't know if it will. Everybody kind of hopes so, and we even imagine a world in which CS24 was taught in Rust, but that's not coming anytime soon because it takes a lot of effort. So anyway, we have unchecked array accesses, buffer overflows, other memory management problems. So it's really easy to leak memory. And you all saw how easy it is on assignment 1. I gave you code that leaks memory. And I was like, oh, yeah. So, we have these issues with memory management. It's not an easy thing to do. And so what people have recognized is, why don't we actually give people less power in their programming languages, because they usually don't need it. I mean, if you are writing a memory allocator, you need all the power of C. But if you are not writing code like that, which most people don't, remember, a few people write that kind of stuff, and then it becomes a facility that everybody gets to use. And so other people don't need to write that code. So why don't we actually give people languages with simplified memory models so that we can make it easier to write correct programs? Okay? So what we're going to talk about a little bit today is one aspect of this, which is implicit allocators. Why don't we simplify the memory model so that people can actually write correct programs more easily? Now, what I'm saying here is that they're safer programming models, so we're taking away power, but that's okay because people don't usually need it, and if they have it, then they'll probably misuse it. It also starts requiring a larger runtime. C does have a runtime, but it's tiny. C++ has a slightly larger runtime. Python and Java and all of these other languages have very large runtimes because of all of the things that are taken care of for programs. Okay? So let's see. So we're going to talk about 3 language features. I already talked about this last time, but today we're going to talk about implicit allocators. Wednesday we're going to talk about object-oriented programming and how you implement objects. Okay, so this is something probably many of you already have some sense of how it works, but we're going to do a deeper dive into it and even explore how you implement polymorphism. So it's pretty cool. A lot of interesting stuff, and then very relevant, for a lot of circumstances, because object-oriented languages are very common. And then we'll also talk about how exception handling works, which is just freaking cool, and not a lot of people understand it, so that's why I like to talk about it. Okay, so we're going to draw from Java, but you should not be 100% committed to that idea, because what you're going to notice is that a lot of the things that we talk about are from a more C-like perspective. And so you can think of it as being C++ and Java is going to be the source of our inspiration for discussing these features. Now today it's definitely going to be Java because Java has garbage collection. C++ does not. And we're talking about implicit allocators. Okay? Now, programs are bad at remembering to release memory when they're done with it. We're being very generous to the programmers who write these programs, right? Because the program is only doing what the programmer said to do. But what we can do is create a memory allocator that takes care of this task, this responsibility on behalf of the program or on behalf of the programmer. Okay? So typically we see this implemented as a garbage collector. And I'm sure all of you have heard of garbage collection, and the idea is very simple. Once a chunk of memory is no longer in use by the program, then the garbage collector comes along and takes it back, which means 2 things. One is, we have to know when the program's no longer using it, And two, the runtime somehow has to keep track that there is still a chunk of memory here. So no longer do we have resource leaks because the runtime keeps track of all resource allocations. And also somehow we need to be able to figure out that the program is no longer using it. Okay? And so this is really nice. It becomes much easier to write programs. And sort of the worst circumstance that you run into with a garbage collector is that some program hangs on to something longer than it should. Okay? Well, it doesn't sound like the end of the world. It may make your program run out of memory faster, and usually the fix is relatively simple. So already this starts to make life much nicer when you're writing programs that do memory management. Okay? Typically, we look at this thing called a reachability graph. Okay, we have objects, they're allocated in the memory pool. Well, you can call it a heap. Some languages call it main memory, but it's a heap. And so we have this collection of objects that reference each other in some way. And so you can define this thing called a reachability graph. Where does it start? Well, there are some things that are global variables. It's uncommon. I mean, I know that always when we talk about programming practices, we say, don't use global variables. Well, it turns out that there's some circumstances where you have to. And usually that's the starting point for your reachability graph. Now, another place that you see a lot of roots, if you will, in this graph is stuff that's on the stack. Your function needs to have a local variable that's an object, and so maybe it allocates something on the heap. Well, as long as it's on the stack, it's a root. And if that function terminates and returns and goes somewhere else, and now that object is no longer on the stack, it's now garbage. Okay? So anything that's sort of in those two locations is considered a root. And so basically, we look at everything that is reachable from the root. Okay? So again, our little picture, we have a box that's labeled root nodes. So these would be stuff that is referenced by global variables or by stack content. And anything that's reachable from that we want to keep because the program may still be using it. Anything that's not reachable, the program can't be using it anymore. Is everybody convinced of that? If the program doesn't know about it, it's garbage and we can take it back. Okay? That's the underlying premise here. So we have this nice little constellation of nodes over here in the bottom right that are unreachable. Okay, any questions? So this is the idea, and somehow we need to figure out what is the reachability graph for a program running in our language. Now, if we go back to where we're coming from, which is C and C++, the question is, how would we do this for a language like C and C++? Okay. This is a really challenging problem. I hope that all of you, when you're looking at this, think, ugh, that sounds kind of terrible. Because we're kind of trying to step out of the explicit allocator world. And remember that we already talked about some of the difficulties there. Somebody mallocs a block of memory, so I hand it to them. And once I've handed it to them, I can't really do anything with it. I can't slide it in memory because they may have pointers into the middle of it. They may have pointers in it to other things. So it becomes really difficult to know what is referencing what in a language like C. We have these kinds of things, pointers into the middle of memory blocks. We've talked about that, pointers into the middle of structs and arrays. What if I have pointers and I decide to start casting them into other types? I'm allowed to do that. All of you are doing that kind of thing for assignment 3. I've got a void star, and I'm going to cast it into or maybe you have an unsigned character star, I don't know, but I'm going to cast it into a header star, and now I'm going to add something to it and cast it into a void star and return it to somebody. Okay, that's totally allowed in these languages. Recasting pointers into integers. There's like a special, remember that on x86-64, our pointers are 8 bytes and ints are 4 bytes. So you wouldn't necessarily cast into an int because you'd lose 4 bytes of your pointer. But there's a special type called int pointer underscore t, which is supposed to be large enough to hold a pointer. You can cast it to that and then cast it back. So this makes it difficult to figure out what is a reachability graph. Okay? How do I know what is a pointer in the first place or isn't a pointer? And then once I know that, how do I figure out what's accessible from other things? Okay? So what we do in these languages is basically identify anything that could be a pointer. You know, even if it's an int. Well, it looks like it could be a pointer, so we're going to assume that it will be at some point in the future. That's kind of all we have. Okay? And so we end up with an approach that's conservative, and that's why we call it a conservative garbage collector. Because if we have something that looks like a pointer, we assume that it is, and the thing that's referenced by it is in use, so we shouldn't take it back. Okay? Now what happens if the thing isn't a pointer? What happens in our world if we're trying to do garbage collection and we find something and we think it's a pointer, but it really isn't? Now here's the question for you. There's another question that we're completely ignoring right now, and I'm just going to acknowledge this up front so that you all understand. How do we make the decision about whether something looks like a pointer or not? Well, all of you probably have had circumstances where you tried to dereference null, right? And your program goes, right? It explodes. Or maybe you have some other value and you try to dereference that and it goes, but it's definitely not null, right? Or maybe you have garbage somewhere and you know, you try to follow a pointer through that and you end up exploding. So there's a lot of circumstances where you have values that you try to dereference and it terminates your program. Well, the operating system knows what the address space of your program is supposed to be. And anytime you try to access something that is not a valid address, the OS will just terminate your program. And so these conservative garbage collectors rely on that kind of capability to say, this is a value, it's pointer sized, and it happens to have a value that falls within a valid address range. Okay? And so the garbage collector can take this even further and say, it falls within the heap, and it happens to fall within a memory region on the heap that is a chunk of memory that I've handed over to the user or the program. Okay? So that it knows this could be a pointer to a region that is in use. So that's the idea about how we say, hey, this looks like it might be a pointer. So then the question is, what if the value isn't really a pointer for some reason? You know, it's just a value that looks like a pointer. Well, it's kind of not the end of the world, right? Because we have two circumstances that could occur when we're trying to do garbage collection in a language like C or C++. We could either decide something is not a pointer when it actually is, and free memory that somebody is actually using, and then we're sad, right? Because then the program will access it and probably crash. Or we could decide something is a pointer when it isn't, and we have an allocated chunk of memory that's actually garbage, and we don't reclaim it. Well, the program will continue running in that circumstance. Right? So we have these two circumstances, and one of them is much worse than the other. And so it's okay if we have a situation where the garbage collector doesn't reclaim something that's actually garbage. It just means that there's going to be fewer resources. Maybe at some point that value goes away and the garbage collector says, oh, okay, that isn't garbage. I mean, that isn't in use. It is garbage, so I can take it back. So you can hopefully see that conservative garbage collectors, they identify anything that is reachable as being reachable. They may identify some things that are not reachable as being reachable. And so the program will run and we'll get some good amount of garbage collection, but maybe not as much as we want. Okay? Everybody see that? So if you're curious about exploring this idea, there are C garbage collection libraries and C++ garbage collection libraries. I can't remember the name, but there's a really popular one. I think it's just called libgc. So if you're curious, then you can search for that and see how to use it. I think Mike Vanier actually has played with it some. But it's probably been a long time ago because I don't think he has done that recently. But I certainly haven't heard him talk about it. But you can see how a conservative garbage collector would work in this very difficult realm of C and C++ programming. Okay? Any questions? Okay, so that's conservative GC. Yeah, so not all garbage is reclaimed. So another thing that we can do is take away all of that power that most programmers don't really need. Pointer arithmetic and even being able to have things like pointers. Okay. So specify rules on casting pointers, disallow casting to and from non-pointer types. So if it's a pointer, the compiler will know or the interpreter will know this is definitely a pointer. And once we start doing this, then we can implement precise garbage collection, where we definitely identify all garbage every single time. This is what we would prefer, right? We'd love to be able to identify every piece of garbage so that we can reclaim everything. Then our program will have plenty of good memory to use for allocations. Okay, so this makes a lot of sense, and this is the approach that's chosen by a lot of different languages. Java is a great example. Okay? Java has this thing called a reference, and you probably have even noticed that if I try to dereference null, it has this value null, which means the reference doesn't refer to anything. And it throws a null pointer exception, which is weird because it's supposed to not be a pointer. It's supposed to be a reference, but it throws a null pointer exception. Okay. So a reference is kind of like a pointer in that it's a way of looking up an object or referencing an object so that you can say, hey, you want to operate on this object I have over here, so here's a reference to it. Okay? And you can think of a pointer as being a kind of reference because it's literally the address of where that object lives in memory. Okay? But maybe what we could do is make this a little bit more opaque. Maybe we could figure out a way to take the reference and say, yeah, it's kind of like a ticket or some token that represents this object, but it doesn't actually hold the address of the object in memory, and we're not going to let programs access that information anyway. We're going to keep it secret. Okay? So this is a higher level of abstraction. We're starting to hide some of the details about where things live. So reference is opaque. Programs can no longer directly access or manipulate the address associated with a reference. Okay? And obviously, if you think about it, like anybody who's done any significant amount of Java or Python programming, both of these languages have references. Okay? Maybe you can figure out how to take a reference and turn it into some kind of hexadecimal value and say, ooh, I wonder if that's a pointer. Yeah, well, you don't know. The runtime hides that from you. Okay? And so it's really, this thing can be manipulated in very limited ways, and that allows the runtime system to start doing things that it couldn't do before. Like move these suckers around. So now we no longer have fragmentation issues. This is extremely important in Java. We're going to talk about Java specifically today. It's extremely important in any language with garbage collection to be able to start shuffling things around so that we can eliminate the issue of fragmentation for long-running programs. Okay? Does this make sense? Great. This is really, really important. Okay, so this introduces another one of these general themes. Remember, we're talking about a lot of general themes in this class because it's a nice introductory class for systems. So we talked about optimization principles. Fast case is common case is fast. Indirection is another really common principle that you see in system design. Basically, I would like to have a way of indirectly referencing or accessing something so that there's some intermediate table that says, this is the thing you want to access. Well, the table says what it really is or where it really is. Okay? So you see indirection quite frequently. Okay? And we've had this already more than once in this class. I just don't introduce it until now because this is one of the most obvious examples. Okay? Branch to register, so now I'm using a register's content instead of having a branch to literal address. Labels as jump targets. You can see, and probably you remember, hopefully you remember, because this class is, we're only in the 4th week now, each one of these things gave us a huge amount of sophistication, like a big jump in sophistication in the way that we implement programs or the things that we can compute. Okay? So references allow me to access something indirectly. The runtime can access things directly. It knows everything, but my reference allows me to refer to something without being able to access it directly, and that gives the runtime a lot of power. Oops. So there's this great statement, which you probably heard before, and you haven't, you're going to probably hear it a lot in the future, which is all problems in computer science can be solved by another level of indirection. Okay? Very true statement. I don't know, maybe it's also a little bit hyperbolic, but it's a very true principle that you'll see in systems implementation. In fact, you'll notice this in assignment 4. Like assignment 3, you all looked at the unacceptable allocator. You remember what it does? Here's a pool. Here's a pointer. You want some memory? Here you go. I'm going to hand it out, and then I'm going to advance my pointer. And then you want some memory? I'm going to give you a chunk and then move the pointer. And so that pointer just moves forward. Guess what? In assignment 4, you get exactly the same allocator. Except what I did was I added a level of indirection to it. So that now you have a reference, and those references all go through a table. And that allows you to move around chunks of memory. So suddenly the unacceptable allocator becomes completely accepted. And it's really cool and powerful, especially once you add garbage collection to it. Okay? So this is one of those interesting things about computer science, is that sometimes you can just apply a slight variation, and something that didn't work well at all suddenly becomes really powerful. Okay? So you see that quite a bit. Now we're going to talk about the garbage collection algorithms that frequently appear in garbage collectors, and there is a very common one called mark and sweep, and its name says exactly what it does. Okay? You have a flag associated with every object. Remember, we have this reachability graph with some roots in the graph, and we need to figure out what the graph is. But don't forget that the runtime knows every single object that's been allocated. So the runtime can access everything. It just needs to figure out what the program can see and what the program can't see. And so it goes through. Initially, all the little flags associated with every object are 0. Okay? And so it has 2 phases. I bet you can't guess what they're called. The mark phase and the sweep phase. So the first phase is to go through and mark every reachable object. Okay? Once that phase is done, then it goes through a second phase, which is look at every object and see which ones were not reached and free them because they're garbage. Okay? So, you can implement this in all kinds of different ways. You probably would implement this not even in depth first. If you were doing a very simple approach, like if you do mark and sweep for assignment 4, you'll probably do a depth first search. But if you were doing this in real life, you'd probably do something clever with parallel algorithms or something like that. Okay. But depth first search is real easy for this kind of thing. But we're doing it breadth first just because it makes for more understandable slides. But we mark the roots, then we mark the nodes reachable from the roots, and then we mark the nodes reachable from them, and then we mark the nodes reachable from them until we run out of nodes to reach. Okay? And once we've gone as far as we can, then we are ready to figure out what's not in the reachability graph. Everybody got it? Super easy. So second phase, we just go through all of the objects, and if its reachable flag is set to 1, we just clear it for the next time we run mark and sweep. And if it's 0 when we get to that object, we go ahead and release it and reclaim the memory. Okay? Does that make sense? Yeah, not a problem, right? This is a pretty straightforward one to implement. So we end up having identified the garbage. Yay, precise. Now, there are some issues with this garbage collection algorithm. Okay? As it would be the case with all algorithms, there may be some strengths and weaknesses involved. It turns out that with mark and sweep, you kind of have to stop everything else from happening while the algorithm runs so that you can actually identify all the garbage. Now, if you have a single-threaded programming language running on a single processor, that's not so bad. But if you have a multi-core system, or you have a system that has threads, well, now you have to stop everybody, even though they could be doing things while you're garbage collecting. So this makes me sad. It's like you would love to have garbage collection going on in the background. And there's a lot of frightening stories that have occurred, but I don't care. I don't care about ballistic missiles blanking out while they're flying and doing garbage collection. That's scary, yes, but what's more relevant to me is when I'm typing my text editor and it pauses for 20 seconds and then I can't type anything while it's garbage collecting. Obviously, that's much more serious. So, so garbage collection can be a big hassle. These are called stop-the-world garbage collectors. Okay? Because they stop everything while they do the garbage collection. The ballistic missile story was told by me by a professor when I was an undergrad, and I sure hope it isn't true. But it's scary. Anyway, if you have a situation where you need the program to continue operating and it can't afford to pause, then obviously mark and sweep is kind of irritating because it's stopped the world. Okay? So you start seeing that there's a number of dimensions that you can sort of analyze garbage collector algorithms on. There's stop the world versus concurrent, so the program is allowed to continue running concurrently. Now, that said, even concurrent garbage collection typically has little points in time where people have to stop doing things, because it needs to make sure that it identifies everything. And so it might have to say to the program, stop this part, and I'm going to do something over here, but then you can resume more quickly. So concurrent garbage collection attempts to make those stop the world phases as small and as limited as possible. Okay? So that's stop the world versus concurrent. Then you have serial versus parallel garbage collection, where basically you imagine during the garbage collection processing, can I use multiple processors or not? If you can't, then it's serial garbage collection. Parallel garbage collection would use as many processors as are available to speed things up. And then the most important one, perhaps, is compacting versus non-compacting. Okay? Compacting takes all that free space that it identified and it smooshes all the objects together and makes sure that the free space is as large as possible. Okay? Non-compacting collectors don't do that or can't do that. Okay. Think about like our C++ garbage collector. You know, we talked about conservative GC. Well, if you have a garbage collector that operates in C or C++ programs, can it compact? Really, it can't, right? Because we may have pointers and stuff that we can't really slide objects around anymore. Okay? Not without introducing a level of indirection. Okay? Compacting collectors effectively avoid the issue of fragmentation by making sure that free space is always pushed to one end of the pool and used space is always pushed to the other end of the pool. Okay? So that's actually a really, really critical one. Okay? So that's, I'm going to leave that up there for a little bit. Are there any questions? So for assignment 4, for example, you are expected to write a compacting garbage collector. That's part of the requirements for the assignment. And I think you'll have a lot of fun doing it. It's kind of really neat. So here's another question to think about. We have this mark and sweep garbage collection algorithm. And the question is, when is it going to be the least expensive? And what I mean by that specifically is it going to be the least expensive when it identifies a lot of objects that need to be reclaimed or a few objects that need to be reclaimed? That's the question to consider. If you think about it, we're going through each object, looking at it individually, perhaps freeing it individually. So if we have a lot of objects dying on it, then there's going to be more work. And think about all the bookkeeping that you have to do for an allocator, right? You're all familiar with this by now because we've talked about headers and footers and this and that and updating the memory pools, bookkeeping data and all of that. Well, if you have, let me not get ahead of myself. Implicit allocators also have to do all that bookkeeping. You know, it's just a fact of life. They have to say this object is this many bytes and it lives here and, you know, blah, 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 right? Compact, blah, blah, blah. So if I have a situation where I'm going through and identifying garbage and freeing those objects, then I'm doing the work of releasing each one of those objects individually. Okay? If I don't reclaim many objects, then it's not too bad. I have to traverse the entire graph, blah, blah, blah. I have to look at every object and see its flag. I'm going to do that anyway, but as long as I'm not having to reclaim objects, it's not too bad. Okay? So, this is kind of an interesting observation, that mark and sweep does a lot of work if you have a lot of objects dying on it. Okay? So this is kind of an interesting observation, that Mark and Sweep prefers long-living objects. Okay? Or let's say we prefer using Mark and Sweep. Let's not anthropomorphize an algorithm, right? So we like Mark and Sweep if we have long-living objects. Okay? So here's another approach that we can use, which is a copying garbage collector. So we will no longer have all these objects hanging out and just allocate them wherever we have space and then run garbage collection and identify unreachable objects and smush everything together anymore. So instead what we'll do is we'll allocate in a space. We'll just have a space that's a pool for allocations. And when we run out of space, we will evacuate the reachable objects out of that space so that we can reclaim that entire space in one shot. This is an interesting approach. Like it says on the slide, all the dead objects get deallocated in one operation. So these are called stop and copy allocators. Okay? You have two regions of memory. This is the one downside of stop and copy, is that you end up with two chunks of memory because one is the one you're using to do your allocations in, and the other one is waiting for when you have to evacuate reachable objects. Okay? So new objects are allocated in the to space. When the to space finally fills up, what we do is we switch the two. So we had one that is a to space and one's a from space. We switch the two spaces. And now we start copying reachable objects from the from space, which just was the to space, just filled up. We start copying all the reachable objects out into the new to space. Okay? And then we can reclaim the entire from space at once. Okay? Now I'm going to go ahead and show this to you in picture because I hate trying to describe things like this in words. So we have this chunk of memory. We had to cut it in half because that's the characteristic of stop and copy. We allocate objects in the to space. Okay? And for whatever reason, my convention was the root of the reachability graph is the first object in the space. So for whatever reason, I just did that. So now it's full. Program stops. And now we just start following the reachability graph. And every time we find an object that's reachable, we copy it into the new to space. Okay, so we start copying these little bad boys over here. Okay. Now you notice that we had two objects that were not reachable for whatever reason. But the nice thing is that we can just say this whole space is now available for new allocations. Okay. So is this going to prefer long-lived objects or short-lived objects? What's going to make it do less work? Where's the work? Yeah, copying objects, evacuating objects is work. So, hey, what if I just have a lot of objects that are dying all the time? We love that, right? Then I have very little to copy. So stop and copy is fast when not many objects live very long. Okay? And because that means that we have fewer objects to copy. You can see that in my example, I kind of didn't have that. I have a lot of objects to copy, which is a drag. Okay? So stop and copy prefers short-lived objects, which is really interesting because remember, I just said that Mark and Sweep prefers long-lived objects. Why don't we see if we can find a way to combine these ideas? We have different garbage collection algorithms, good for different circumstances. So the question is, do all objects behave the same when it comes to garbage collection or their lifetimes and so forth? Okay. You can think about a language like Java, and maybe you can now think back on your experience using Java if you are very experienced using Java, or Python, which is exactly the same, and think, well, do I create a bunch of objects that I immediately don't need because they're for temporary values or something like that, intermediate values in a computation, and then I don't need them anymore? What objects do I actually keep around a really long time? Okay? So you can imagine that you have this interesting, let's say, landscape of how different objects' life cycles are and how they behave. This is where generational garbage collection comes into the picture. Okay? It turns out if you look at, and again, this is one of the nice things about writing runtimes and writing programming languages, because then people write applications and you can download their application, instrument your runtime, and just let the application do its thing and analyze what the application does. So you get real-world data, practical data about how the program is behaving. And so the observation is most objects in a program are short-lived. They don't last very long. And so this is stated, some of the research papers are kind of scary to read. Most objects die young. Okay? The long-lived objects don't reference the short-lived objects hardly at all. If they did, they wouldn't be short-lived objects. They'd be long-lived objects. Okay? So there's kind of this separation in the program state management where you have short-lived objects that maybe reference other short-lived objects and long-lived objects that get updated infrequently and they don't touch the short-lived objects. So this is called the generational hypothesis, and like I said, it's also called the infant mortality hypothesis, but I don't like that at all. So, okay, so here's the idea. We will design a garbage collector that takes advantage of this behavioral characteristic of most programs, and it's called generational garbage collection, and this is a great example of saying, hey, what is the common case of the computer programs that are run using my runtime? Why don't I make that common case fast? Okay. So this is what, and I don't know if hotspot is still, Sun is definitely not the right term to use anymore because Sun got acquired by Oracle. And there's been pretty consistent development on the Oracle Java virtual machine by now. But the idea of generational garbage collection definitely still makes an appearance. So this is still relevant information. But the idea is the garbage collector divides objects into young objects and old objects. Every object kind of gets an age associated with it. What's the age? Well, maybe how many GC passes it's lived through would be a great example of what an object's age can be. Okay? So we have these various spaces. And the very first space that an object is allocated in is called Eden. Eden is the initial place where objects are allocated. Okay? And then we use stop and copy with Eden and our other memory areas. You can see we have two quote-unquote survivor spaces. And so this is where objects are allocated. And the idea is that most of these objects will be immediately reclaimed in the very first garbage collection pass. So Eden is always just like wiped out. We only evacuate objects down into the next collection of spaces, the stop and copy spaces. Okay? So those then go into a short-lived object memory area where they're managed using stop and copy because the presumption is they're not going to live very long. Okay? Everybody got it? So that's the very first approach is we have Eden, which is used for the shortest lived objects, and then we have stop and copy for the short-lived objects. Okay? Now, like the slide says, these survivor spaces are designed for young objects, but they're not immediately born, you know? So they're objects that have been around for a few garbage collection passes, and so they're basically given more time to either demonstrate that they're going to stick around or they're going to be reclaimed. Okay? And again, the way that the research paper describes it is we'll give young objects additional chances to die before they're considered old objects. Okay? So they go back and forth between the from and to spaces. Okay? So, and this works exactly like what I described before. To space fills up, that's where the objects are moved from Eden. So you have Eden, Eden fills up, you wipe it, and you do your garbage collection. You evacuate objects into the to space. When the to space fills up, you do garbage collection on that space, evacuate the live objects, reclaim the to space, or the old to space. Now it's the from space. Okay? So you're doing this, and it loves that almost all of its objects are dying because then it's super fast. It has very little to evacuate. But every once in a while, you notice that there's objects that have been through quite a few GC passes. Okay? And so what happens is instead of evacuating from the from space into the to space, it says, you know what, this object has been around. maybe it's long-lived, and so it moves it down into the old generation. Okay, so that's how generational garbage collection works. Is based on the age of the object, it will actually choose where it should go, and then these different regions can even be managed with different algorithms. Okay, any questions? I don't know if any of you have ever tinkered around with Java management capabilities of a Java virtual machine. I'm sure you will have this experience. If you do any significant amount of Java programming, you'll do this eventually. But you'll notice, like, one of the things that you can monitor through the Java Management Console is the current memory utilization. And it's pretty wild because you watch it, and especially if you have a program that's doing a lot of computations, you'll see the memory allocation, and maybe you do things, and it starts to go up. But you'll see it actually goes up like a sawtooth. But it keeps climbing up and up and up and up, and then all of a sudden it goes wham, and it drops way down, and it starts climbing up again with a sawtooth. You'll see things like that in the behavior. Well, what it's doing is it's running garbage collection passes on different spaces in the generational GC implementation. And that giant drop is going to be when it clears all the spaces. And it goes and it looks, is there anything in the old generation I need to reclaim, and so forth. Okay? So you see this behavioral pattern in the virtual machine, the way that it runs. It's a very sophisticated approach, which I have to say I'm happy. Because when I was using Java 1.0 and 1.1, people were saying, Java will never become successful because garbage collection is too slow. And I was really irritated when I was using my Java development environments because it was too slow. Now it's really nice. It's much faster. Okay, so young object garbage collection, Eden and the from space are now empty. Okay, so you have the to space contains youngish objects. Old generation contains old objects that have stuck around for quite a while. Eden is empty, so I can allocate more young objects. Okay. So yeah, the benefit of using stop and copy, I think it's obvious, the benefits of this approach, right? You have most of your objects dying right away, so you stop and copy for the young objects, and then we move things out when it seems like the stop and copy algorithm is not most suited to the lifetime of the objects. We move it down into an area where we do compacting, mark, and sweep. Okay? Let me see what else I say about this. Yeah, so the old generation will need periodic garbage collection. We do expect most of these objects are going to survive. So, I mean, it's the old generation, right? So we don't use stop and copy for that. We use compacting, mark, and sweep. Okay? Are there any questions? I hope you're all as impressed by this as I am. I think it's a really good design. The only other thing I will say is do not implement this for assignment 4, because you'll make me sad. You'll make yourself sad. You get to pick something simple. So you'll either do compacting, mark, and sweep, or stop and copy. Those are the two choices that people normally make for that assignment. All right, let's see. What else is there to say? Yeah, so this is complicated, but it does take advantage of a number of important details, which is that we have algorithms that are good in different circumstances, so why don't we try to engineer the implementation to take advantage of the best algorithms for the best circumstances, okay? And also this weird thing that programs have this particular behavior. You'll even see this in functional languages. Like, functional languages are notorious for saying, make a value and now it's read-only. And if you want to modify something, well, you make a new value with the modifications, and the old value is now garbage. And so you have a really neat characteristic that in functional languages, this is even more exaggerated than you would see in a language with state mutation, in-place mutation of state. And so these kinds of garbage collection techniques work really well across the board. They're really powerful and useful approaches. Okay. So this is yet another example of a common theme that you'll see in computing systems. Okay? You'll see this again later in this term, and you'll see it again in CS 124 if you take 124. That you have these specialized solutions, and a lot of times you can figure out multiple ways of solving a problem. And you know that those solutions work well in specific circumstances, but then we want to be good at the general. And so you find ways of combining these special solutions into a more general approach. And so this is a really neat thing when you see people achieve it, it's usually really impressive because a lot of times there's an elegant way to blend multiple approaches into a single solution that is very powerful in a general way. Okay, so that is a common theme. Okay, questions? All right. Let's see. Last thing to talk about is reference counting, which some people don't consider to be garbage collection, but my garbage collection, I have a whole book on garbage collection. It's such a great book. It's expensive and it's hard to read, but it's a really interesting book. So, but, you know, they talk about garbage collection and reference counting as well. So this basically uses a different approach than maintaining or identifying your reachability graph. Okay? So every object keeps a reference count, and a reference count is just how many other objects are referencing me. So I've got like pointers coming in, and that is going to just be a count of how many objects are pointing to me. Okay? So you create an object or you receive an argument that increments the reference count. When you're done working with the object, the reference count is decremented. Okay. Now, languages that use reference counting for memory management will do this automatically. Like, you don't have to think about it. But you may also happen to work in a language like C or C++ where you do have to manage this stuff manually. Back in the 90s, when I was working for Microsoft, a lot of the code was written in C. C++ had a lot of warts still back then. And we did reference counting. And we had to do it manually. And if you forgot to do it properly, then you leak objects and you get scolded and you'd have to fix your code. Okay? But reference counting is very powerful and a very widely used approach. Okay? So yeah, when the reference count hits 0, it's automatically reclaimed. Okay? So you don't have DC passes anymore. You just have reference counts hitting 0 and objects being reclaimed. Okay? Now here's the issue with reference counting. Let's say that I have a cycle. Well, now I'm sad because the cycle is sort of self-sustaining when it comes to the rules of reference counts. Right? Everybody see that? Our little chunk of garbage. It's like a floating island of garbage. We have those too in real life. So we have this little chunk of garbage over here, and everybody's reference counts are 1. But really, we know it's not reachable. So this is the one downside of reference counting. Now, you might think that would be sufficient to cause people to not use it, but it's still used very heavily. In fact, the most, probably the biggest use of reference counting as far as widespread usage is Python. Because we all know how many Python programs are out there running, and I know I've written a ton of Python code. Well, Python uses reference counting for its memory management. It has this issue. So how do you deal with this? We have a cycle. If we could break the cycle, then we might be able to reclaim that memory. So one is to start getting some of the cleverness that garbage collection has, but not too much, because we don't want to be too clever, right? And so the idea is, if you have this collection of objects that are keeping each other's reference counts at 1, then can we find ways of identifying those cycles so that we can break the cycle somehow? Okay? And so the premise is that since I'm doing this infrequently to identify cycles of objects, which hopefully will not happen frequently, then this won't be very high overhead. Okay? This is what Python does. It tries to identify cycles periodically. Okay? How do you identify what could be in a cycle? Well, maybe you have things that haven't been accessed recently. Maybe you have things whose reference counts haven't changed in a long time. You could look at things like that, and that might give you a clue about what could be part of a cycle. And you look at those. Okay? So, works for Python, I guess. Maybe it's okay. Here's another one, which I detest. Unfortunately, it's also one that I've had to use more than once in actual coding projects. It's powerful, but it requires upfront design. We have this idea of a weak reference. A weak reference is a reference to an object. The reference does not increment the reference count. What could possibly go wrong, right? I've got a weak reference to something. It may go away. So, weak references are a little bit dangerous. Okay? And so a lot of times when you have a weak reference to an object, you don't really have a guarantee that there is an object at the end of that weak reference. That's the fun challenge of dealing with weak references. Okay? So it does break cycles. And I say here it properly breaks cycles. It only breaks cycles if you have designed your program properly to use weak references. And that's the thing that I find really irritating about it, is that you have to think a lot harder as a programmer to use weak references than you do if you use garbage collection. You know, a proper garbage collection algorithm. Okay? So that's the issue with this, okay, is that you have to think carefully. And I'm a giant fan of not having to think very carefully, because it means less likelihood to make errors. Okay, any questions? Alrighty, so let me see what I say here. Yeah, so there are other ones. Oh, you would be shocked at how much overhead there is in updating these reference counts. We haven't even talked about all the ways in which this is extremely costly, okay, because we haven't talked about caching yet, processor caching. But that has a giant, like a humongous impact. There's this big section of my little garbage collection book that talks about how to deal with that. And it is so complicated. So yeah, it is easy to implement, blah, blah, blah. Okay, so implicit allocators are great. I think all of you, having used C a lot and going to be using C even more in this class, probably will love languages with garbage collection even more after you're finished with this class, because it really does make life a lot easier. Okay? So we simplify the abstractions, we take away power and capability, but most programs don't care. Okay? And so we use garbage collection and blah, blah, blah. Okay? So that's why we would want to have references instead of pointers. Okay? So I'll see you next time.